Build Show Live 2024 conference classes are brought to you by Builders First Source, Huber Engineered Woods, Pella, and Sashco. This session is sponsored by Polygaurd.
Hey everyone, I'm Zach Detmore and I'm here at the first Build Show Live. And none of this would be possible without our amazing sponsors and partners in this event. If you're unable to make it to this one, we are going to have another one next year in Dallas in 2025, so hope to see you there. But I want to take a moment to call out Sashco. If you're unfamiliar with them, they've been doing this for about 85 years, specifically making super high quality sealants and caulks. The lovely thing about them is they're focused on the end user. They have the customer at top of mind, and that's why I like using their products, because they're easy to work with and they're durable. I'm always concerned about warranties and callbacks, and having a failed sealant is really something that can be expensive because it usually involves repainting or disassembling things, and I don't want that. I'll give you an example to sort of help you understand the difference. So if you think of a fiberglass tub, for example, the fiberglass tub is here, and then you have the tile coming on top of it. And in New Jersey, where I build, for example, if we frame something in the dead of winter, the humidity is very low, so that framing member is sort of compressed as small as it will be. And then come, the middle of July, when it's super humid, it expands, and what happens is the gap between the tub and the tile can open up. And also when you're getting into a tub or you're loading a tub with water, sometimes the fiberglass will come down, maybe you don't have a perfect bed of mortar below your fiberglass tub, and you get movement. The point is, houses move. And if you have a sealant like this, which is sort of probably very commonly used, you'll notice it is stretchy, right? But the thing is, it takes a tremendous amount of force for me to keep this tension. It wants to return back to its previous state. Versus if I use some of the Sashco products, this is actually very stretchy, much more stretchy, but the cool thing is it sort of relaxes in this stretched state. So it's much more likely that this is going to remain bonded to the tile and to the tub and remain waterproof through sort of the life cycle of the house. And it's very common for me to have to come in and remove poorly installed sealant because of this exact issue. And that's really why I use the Sashco product line. They have a product line for everything from roofs to windows, and they make a product for each specific application. So if you're unfamiliar with their products, actually click the link in the bio and they'll send you a sampling of any one of their products for you to try out. I highly recommend it. See you at the next Build Show Live.
Good morning, everyone. How are you today? Great. I know what I plan to talk about for the next hour. Why are you here? I know. What are you here for? What do you want to talk about?
I want to find out more about controlling heat pump water heaters.
So, controlling heat pump water heaters. Anybody else? Recirculation?
Yeah, I want to set up the house efficiently. I just have knowledge how to. We design our HVAC systems. Why don't we design it?
So you want to design the plumbing systems to be efficient given the floor plan. Yes, in the back?
Right-sizing pipe.
Right-sizing pipe? Tankless what? Okay.
Condo unit, high-end.
Got it. So tankless, right? Anybody else? Yes.
Water manifold or not?
Water manifold or not? Do you mean a home run manifold or a mini manifold?
Home run.
Got it. We'll cover both, home and mini manifold. Yes, sir. Dual tanks or one big tank? Okay. Tankless water heaters? Dual tankless water heaters. They duel, by the way, D-U-E-L. They fight each other.
Yeah.
So on-demand motion sensors or smart sensors for controlling recirc pumps. Okay. Anybody else?
Bring more value to clients.
Bring more value to clients. That's good. Yeah, one more. You're good? Anybody? We're good. All right, we'll get started. What? New technologies. There are always new technologies. So I'll give you the first answer. Everybody who sells a new technology tells you they have the best thing since sliced bread, right? That may be true, but we're making sandwiches. We're putting a whole bunch of the best things together to make a good sandwich. If it doesn't make a good sandwich, it doesn't matter if it's the best thing since sliced bread. Got it? We have to figure out how to put it together because the customer gets the result of all those things. All right, let's move forward. Slide up, please. Have you ever heard anyone complain about waiting for hot water to arrive? Cool. Me too. Do you want to know how to fix it or prevent it? I like to prevent problems as opposed to fixing them, but you got to figure it out. All right. I have a set of objectives for us to cover today. You can call it an outline, whatever you'd like. And we're just going to go through it step by step. How long do you want to wait for hot water to arrive? I'm going to ask you a question. And then I'm going to need about 10 volunteers. Okay? Because we have a demonstration for us. How long do you want to wait for hot water to arrive? Okay.
3 minutes for a cold shower, then.
So 3 minutes for a cold shower, 5 seconds in the back, 0 seconds. All that's possible, right? 0 is very, very hard to build. You can't even do it with a recirc loop. 0 is really, really hard to build. It is possible, but the technical answer to 0 is that the heater is in the faucet or the shower head, and it's already hot. If it's not already hot, it takes more than a second to get hot. 0 is really hard to do. So short is possible. Is that fair? I'm going to count seconds, 1, 1,000, et cetera. You all have to yell out and scream when you want the hot water to arrive. Are you ready? 1, 1,000, 2, 1,000. You didn't get me very far. All right. You're a tough crowd. So the normal answer I get is 3 to 5 seconds. I've asked this question of 50,000 people in the last 30 years in groups just like this one. 5 seconds is a pretty typical answer. 2 is tight, by the way. It's possible, but it's hard to do. I'm going to teach you practical plumbing today. Don't make your life miserable, make it really good. And I think of it as horseshoes and hand grenades. Getting close gets you points. Everybody happy here? All right, so I need some volunteers. Who thinks they might be the tallest, who thinks they might be the tallest person in the room today? Come on, somebody's got to be over 6'2" in this room. Has to be true. All right, 6 foot. I need somebody. Come on, you got your hand up first. You come up. Who wants to be a water heater? I need a water heater volunteer. Come on, you can be the water heater volunteer. All right, who thinks they might be the shortest person in the room today? Water heater, go stand on the corner. Get out of here. All right, you're the tall one. You stay here right in the middle. Who's the shortest? Come on up. That's great. You stand next to him. All right, now I need a whole bunch of volunteers. Just start coming up. I'll tell you when we have enough. Come on, I need volunteers. This is true. All right, you give him one end of that. No, he gets one end. You don't get the other end. Give him one end. You're the water heater. Hold the damn pipe. There you go. You go that way. Take the pipe, go that way. Walk as far as you can. Here's another one. Give him one end and walk the other way. Not him. He's got that pipe. You can have this pipe. Give him one end and walk that way. Great. All right. Short dude. Tall dude. I need a volunteer for this. You can stand right here, come under here. You're better off being underneath. It's all good. All right, you guys are going to have to move. You guys move this way. Tall dude, come here. There you go. Come over here, stand right next to him. That's perfect. All right, I need somebody else. I need 3 more volunteers, please. Great, Reese, take that. Hold those together. You hold those. And I need 1 more volunteer, please. Here you go. You can do it. You don't need glasses for the volunteering here. It's all good. All right. All of these pipes, if they were full of water, would have exactly the same amount of water in them. How much might that be?
1 pint.
I hear a pint. Anybody have another number? I hear a gallon. Not together, each one alone. So I heard a gallon. I heard a pint. What else? Anybody for a quart? Anybody vote for a quart? Anybody vote for a cup?
1 cup.
Anybody vote for a cup? 1 cup. I'm going to teach you how to deliver hot water wasting no more than 1 cup after you turn on the tap. Why would I bring quarts? We need to look at it. You wanted it in 2 seconds. You can't have a lot of water in the pipe, right? We all good? So you've got the long, skinny tubing. How long does that look like to you? Pull it straight. Come on, pull it straight. Very good. It's almost exactly that. It's 1/4-inch tubing. Can you use it?
Not by code.
You sure?
You said this in the podcast.
Codes don't like skinny tubing behind the walls because they were written in 1940. Flow rates were different then. We have a lot of half-gallon per minute lavvy faucets running around. We use 1/4-inch tubing outside the wall, right? We feed it to refrigerators, ice makers, all sorts of things get 1/4-inch tubing, just not behind the wall. Well, why not? The angle stop from the sink to the faucet, it's a 3/8 fitting, it's a 1/4-inch tube. And if you look at modern kitchen sinks, I'm sorry, that little tube that goes up to the sink is less than this. So it's not really an issue from the performance point of view. You have to make sure there's enough pressure to make everything work at the other end. It's residual pressure that matters, and since nobody knows what's going on exactly today with your real pressure, a little bit bigger pipe saves your bacon, basically. Okay? But there's no reason not to use 1/4-inch tubing. Remember, if it's a hot and cold faucet, you're only getting half the flow on each side or a little less or more. It doesn't need much diameter. It's not moving very fast. So 1/4-inch is possible. There are at least 2 houses I'm aware of in the United States right now that are using it for their fixtures other than tubs and showers and toilets. Toilets have a high flow rate, 1/4-inch tubing doesn't go well. Okay? If you have 1.5 gallons per minute in 1/4-inch tubing, you'll lose 1 PSI per foot. If you're starting at 60, that means 20 feet away, it'll be 40. If that's all you have to get to your fixtures, you're okay. We all good? Moving on. Who's got the next one? You've got the next length of pipe? How long does that look like to you? How about 17? Good answer. It's 3/16 tubing. It's a bit bigger. It could do 2 gallons a minute. Almost 2.5. That's all our showers and faucets in the whole house. We don't need fatter. The problem is fittings now. Okay? All right, you've got the next one. Who's got the blue pipe? How long does that look like to you? Maybe 10. How about 12? Good answer. Yeah, that's good. So it turns out that the 3/8 tubing is allowed in the International Plumbing Code for faucets and showers. And they allow it for sorry about that. They allow it for toilets too. I don't recommend it for most toilet applications because the fitting pressure loss is very high at 3 gallons per minute, and all of a sudden you have the pressure loss of the tubing plus the pressure loss of the fittings. And if you're on the 3rd floor of an apartment building, it becomes problematic. So I like to stay with 1/2 inch for those. But you can use it. This is allowed, but not in Uniform Plumbing Code world because they don't really like you to go below the minimum diameter. You can ask for alternate methods and means, and you can get it if you make the right case, and I can show you how. Okay? You just have to make a case that makes sense. All right. You are 5'2"-ish. Okay. I was. What?
Yeah.
Close.
Close.
All right.
Answer.
Good answer. And Joel, you're about 6'1". Okay, you're a little over 6. The hat's giving me trouble here. It's all right. You're allowed. Keep the hat on. This is 1/2 inch copper tubing. These are 1/2 inch CPVC and PEX. Okay? American adults are mostly the height of 1 cup of water in 1/2 inch plumbing. Anybody like beverages other than water? Which one? Okay, I'll cover beer and scotch for you in a minute. All right, who's got the 3/4 inch pipe? You have the 3/4 inch pipe, Gustavo. I'll hold it up so they're all splayed at the bottom. I want to see them all. How long do those look like to you? 2.5 to 3.5 feet, somewhere in there? Cool, good answer. That's a pint. You're the height of a pint of beer in 3/4 inch tube. Pretty good, right? I'll come back to Scotch. You've got the 1 inch tubing. How long does that look like to you? Yeah, 18 to 24 inches, something like that. Sounds about right. Who's got the 1 1/4 inch tubing? And the 1 1/2, right? You got the 1 1/4 inch tubing. How long do they look like to you?
9 to 12.
Yeah, close. You've got the 2 inch stuff.
7 to 8.
Yeah, 5, 6, 7, 8 inches. That's about right. All of these pipes, if they were full of water, would contain 1 cup. Here's the kicker. If you want to waste no more than a cup while you wait, you cannot have more than 1/2 cup in the pipe that's not hot. It's hard to get close. You've been talking about recirc loops and bringing the loop close to the fixtures, right? We can do that, but in order to get close, you've got to get close. It's possible. When you're plumbing from below up, it's really easy to get close. When you're plumbing from above down, it's hard to get close because the ceiling is way up here, okay? And you have to get close to the fixtures to get the time to tap to come down. All right. I think we've covered all of it for now. We don't have enough time to do the 18 things we'd love to do. Give these people a big hand. Put the pipes back in the, you grab all the coils and wrap them up. You grab the coils, wrap them up, put them here on the floor. Cool. All right.
What about the fitting loss in 5/16?
What about the fitting loss in 1/4 and 5/16 tubing? Don't use insert fittings. Just don't do it. There's way too much pressure loss. Use an external fitting, okay? All right, let's keep moving. We have a lot to cover still. All right. Oh, I want to finish this. I do all my design work at 1 gallon a minute for current faucets and showers and fitting fixtures in the US. Why? Everything is trending down, not up. And I want to make sure that the plumbing will be good for the consumer for the next 50 years. I'm figuring that's at least the life of the plumbing, okay? We're still tearing out galvanized pipe that was installed 80 years ago. Stuff sticks around, okay? So I want to make sure it's good for the future, and I don't see anyone raising flow rates in the future. I see public policy going the other way. So I'm trying to anticipate that a little bit. If you know you're installing lower than 1 gallon per minute devices, use the 1/4 gallon per minute flow rates to start your design work with. What this graph tells me is that if I want hot water to show up within 8 seconds, I can't have more than 8 ounces in the pipe, 1 cup. If you want it to come in 2 seconds, you can't have more than 2 ounces in the pipe, which I would stipulate is up to your knee in 1/2 inch tubing, even less. It's really hard to get that close, okay? It's possible, but you have to really do a good work with both the plumbing and with the design. I'll show you design in a minute. All right, we're going to discuss the benefits of architectural compactness. Does anybody recognize the following house? Water heater in one corner, furthest fixture in the diagonally opposite corner up 2 stories. Anybody ever seen that? Okay, isn't that what we're allowed to build? Because everybody does it that way? I think, are there any architects here? It's all fair game. I'm going to pick on you a little bit, but not badly. You can admit it now. It's all right. No, it's all good. But I think there's a problem on... Does anybody remember the movie Santa Claus? Yes, Tim Allen. I'm thinking of the scene when he's meeting the head elf, and he wonders how come he's Santa Claus. And they get out the really big magnifying glass, and they look at the fine print, the line around the name Santa Claus, and it's fine print, really fine print. And it says some version in legalese of if you put on the suit, you're the big guy. I think there's a clause on the architect's diploma or license that says, thou shalt put water heaters as far from fixtures as physically possible, or you will lose your license. What do you think? Might be there in really fine print. Okay. I've been trying to study how to improve hot water system delivery for 30 years. The only way to reduce the time to tap is to reduce the volume in the pipe. There's only two ways to reduce volume, length and diameter. We just covered the diameter piece. What about the distance piece? We're given plans that says, make it right. Everybody gets that, right? We rarely have control over the design of the whole plan. Sometimes we're lucky. So our job is to make it work so it doesn't leak. That's nice. That's the second piece of the puzzle. The first piece is to get the distance better, all right? So architectural compactness is a concept that says we take a rectangle, we surround the wet rooms and the water heater with a rectangle, only to the fixtures. Notice we didn't go the breakfast nook. We just covered where the water would go to the sink in the island, all right? And we compare that rectangle to the area of the home or the building. It doesn't really matter what it is. In this case, the ratio is 67% of the floor area is related to the hot water system. Okay? We can apply that to any home we're interested in. It can be apartments. It doesn't really matter. The math holds all the time. It's a ratio. It gives us a sense of how far things are apart from each other. All good? Yes, sir. You do a projected floor plan and you take whatever's worst. Yeah, you do it. And yes, it's a plan view, and you get to do your proportions from plan view here. This is the logical worst case. The logical worst case is the water heater's here and the furthest fixture's over there. I've seen 155%. How did they do that? Well, modern house, 3-car garage, that's pretty typical. Water heater on the far side of the garage. A really nice big courtyard and a casita on the other side. That's how. And by the way, the furthest fixture was diagonally opposite the main house too. That's how it happens. That particular house needed 3 water heaters. Well, I want to pay for 3 water heaters. It's a $5 million house. Get over it. Okay, we spend more on the tile in the bathroom than we spend on the entire plumbing system combined. The tile in the bathroom. Forget the kitchen. Okay? Let's be clear about what we're aiming for. We want our systems to work right. Okay? All clients deserve it. All right, I need some volunteers. I need 6 volunteers, please. Come on, I need everybody to the back of the room while we do it. Come with me to the back. Volunteers, and then everybody else come. You're going to want to see this. You're going to volunteer? All right, you want to be, how about you be a washing machine? Okay. You stand over here. Face him. All right? I need a sink. Come on, you can be a sink. Right here, face me. I need another sink. You be a sink, face that way. Stand a little bit, stand over here. There we go, stand over, a little farther. He has to see the line. All right, I need a shower. I need a shower. Come on, over here, face outwards. I need a kitchen sink, please. You can be a kitchen sink? That's right, stand right here, Juan, right here. You can face him because that one can see you. All right, this is the wet room layout of the best architecturally compact floor plan I've ever seen. I'm looking for good ones. I saw the second best I've ever seen this morning here at this conference. Okay? This is a 2-bathroom, 1 laundry room, 1 kitchen house that has been built between 1,200 and 1,600 square feet, single-story slab on grade. They put a tankless gas water heater over one of the toilets in this bathroom. They put the mini manifold, the home run manifold over the other side of the other toilet here, and they ran the pipe sideways in the wall. Virtually no vertical difference. The furthest fixture is less than 10 feet of pipe from the water heater to the furthest fixture. Hot water consistently shows up at all fixtures in less than 15 seconds. If they'd used 3/8 tubing, it would be there in less than 7 seconds. That's getting pretty darn good. That's the best we've ever seen. You're standing and doing it. Yes, sir?
So with the tankless water heater, minimum flow rate to get it to turn on, the smaller diameter tubing, does that become a problem?
So the question is, if you have a tankless water heater and smaller diameter tubing, does it have a problem at reaching its minimum flow rate? No, because skinny tubes carry minimum flow rate just fine. They have reasonable velocity. If you make sure the pressure loss between A and B by fitting choice is not bad, and we know how to do that, right? Then there's very little pressure loss, and it will turn on. If the minimum flow rate is a heat rate problem. If you don't have enough flow to take up the delta T that the burner makes, it'll shut off. It's protecting itself. Okay? You need enough flow to make all that happen. That's why I think all water heaters need to have some amount of stored volume. It doesn't have to be big volume or small volume, zero volume. It has to be somewhere in the middle. And you want a reasonably high flow rate. Yeah?
Another tankless water heater question. So then, with the smaller diameter piping, less volume, same flow rate, can we then size our tankless water heater smaller to meet the same demand?
Not exactly, no. Because you have the gallons per minute regardless of the diameter of the pipe. Gallons per minute is a flow rate question at the end of the pipe. I'll show you some stuff on that in a minute, where the control comes from. We're worried about residual pressure through the system to the fixture. And I'll cover that in a little bit too. But the actual flow rate is not dependent on the diameter of the pipe. It's depending on the control at the other end. Mostly. There are cases where you can really mess it up. All right? This is the best we've seen. I'm looking for number 2, and I want to see people start building them. You want to do 2 stories? Go right up. I got 4 wet rooms. 6. I can have an apartment right above me. Everything goes up. What if I had one water heater for a whole stack? Right? The distance of pipe is very, very short. Short, small diameter gives you the best answer. Not too small, has to be right size. This is the Goldilocks principle. All right, everybody sit down. Thank you. Give these people a big hand. We good? Yeah. All right. I hope so. It's time to take another drink. All right. Everybody ready? All right. Has anybody had a wimpy shower? Wondered why? Okay. So do I. I wonder a lot. Here's the problem. We'll take a 2nd-story shower, and we're going to track where the pressure losses come from, not including what happens in a tankless gas water heater at high flow rates, okay, because of the way they structure their system. No harm, no foul. You've got to figure out how the best thing since sliced bread works in the sandwich. Remember this, you got to put it all together. So we're going to count elevation pressure loss. You have no choice. You go up, you lose some. We're going to go through a tub shower valve, and we're going to have losses in the piping. And I picked the sum of all those to be 40 psi of loss from whatever pressure we start at. How many here know folks on a well? Have friends on a well, right? What's the starting pressure if you have a well system? 30, 40, 60 maybe. Usually I hear about 40. I didn't put that on there. I'm losing 40 to my fixtures. You have a problem if you only have 40 psi to start with, because these losses are independent of the starting pressure. They're a flow-related pressure loss. Okay? So 80 psi is what the plumbing code allows you to put in buildings these days. You can't have more than 80 psi at any fixture. Once you get into the house and go up 2 stories, you cannot have 80 psi at your shower. It won't work. It won't happen. Right? Here's the kicker. Showerhead flow rates are rated for their flow at 80 psi. That's the product standard. So there's no way to get it. No wonder people are annoyed. It can't happen by physics. The other stuff is extra. So what do we have here? We've measured the pressure loss in modern pipe and fittings. I have an entire presentation on all of that. We've got 70 different combinations of pipe and fittings for 1/2 and 3/8 tubing. Okay, different materials, different fitting choices, mostly elbows and T's, because that's most of what we use. And what we have found is that the pressure loss through a given fitting, one fitting, like an elbow, depending on if it's copper or insert plastic, varies a lot, as you can see in the table. And we've done it for 3/8 tubing as well, because that's where we're headed with diameters, right? It matters a lot, okay? So my 20 PSI of pressure loss through the piping and fittings is 20 PSI. That's not irrational given the way we're building. Someone had talked to me this morning about minimizing the number of fittings in the building. That's a really good idea. Okay? We're starting to.
PSI, is that general code across the U.S.?
Yes, it's maximum general code across the United States.
Okay, if you've got over 100,
You're supposed to put a pressure regulator on. Now, my friend the plumber, who's been doing renovations for 55 years, says he likes 70 PSI. Fewer things go wrong if you lower the pressure a little bit. Okay? And
put strain on the joints.
yeah, you put strain on everything if you have a high pressure. So relax it a little bit. But that means it's even harder to get what you want at the shower. You have to pay a lot more attention. So we also went and we measured standard tub shower valves, the stuff behind the wall. And we found, you can sort of see it in this graph. It's a little hard, I'll point it out. This is a US legal flow rate for showers. We have to stop calling these low flow. They are the law. We're not supposed to buy any others. I'm old enough to remember when flow rates were higher. This is now the new reality, okay? So I don't know if we like them or not. That's a whole separate discussion, right? But it has nothing to do with the flow rate. It has to do with how it's designed and how it feels. If we have enough residual pressure, it will work right. This shower valve loses about 6 PSI, maybe 8. And this valve loses 26 PSI through the valve, flowing at the shower head flow rate. That's a big difference. Which one's in your building?
Is there a brand or is it all across brands?
This is across all brands, but these are specific brands.
Yeah.
And so I'm trying to be nice to our industry. It's a design question inside the valve. People are making decisions, and those decisions result in these answers. So you need to know how to pick. Fair enough, right? I want to specify pressure-independent flow regulators for faucets and showers. Why? Once we've built the building, we have no control over what the pressure will be at the house that day. Unless we have a booster system built into the building, we're not in control, the city is. At any given hour of any given day, the pressure is X. A minute later, it's Y. And we have no control over it. So we want to have something that protects us from what happens on a daily basis. This is looking inside a shower head. Notice the O-ring inside the blue ring. That O-ring adjusts in size based on the available pressure. When the pressure's low, it relaxes and the holes that are around it get bigger. When the pressure's high, it closes down a little bit, but it gives you the same flow. That's the special thing we're talking about. If you follow the gray line, if you cut the pressure down from 80 PSI to 40 PSI, you'll only have 1.4 gallons per minute in a shower head that was rated at 2. And if you only have 20 PSI, which is not uncommon, you're only going to have 1 gallon a minute coming out. No wonder people are screaming. But if you put in a flow regulator like this, which are available, you can buy them off the shelf today, you just have to know to ask, you'll follow the green line for performance. Which one do you think your customer would rather have? Closer to what they bought on the box. Fair enough? That's the basic idea. Yes, sir?
Can you put that in if the guy doesn't know
Yeah, it's this big. You can make an adapter. Look, I know people go in and pull out the aerators and they get rid of the fixed hole because it's a tiny hole with pressure behind it. They're not crazy, okay? Go ahead, take that out and they make a little device that's an adapter that has one of these in it. And it will give you constant flow at a wide range of operating pressures. Cool, right? It's a great answer. That costs about $5 for that little adapter, but if you buy it as part of the shower head, it costs you nothing extra to buy, okay? The shower head choice of force and spread matter. It's not so much about the flow rate, it's how it feels when you're in the shower, okay? Here's the one I want to talk to you about for faucets. Notice the different color codes. Okay? The one at the bottom is 2.2 all the way up to 0.375, 3/8 of a gallon a minute. Okay? The ones you can't see through are fixed orifice. They follow the gray line in this graph. Right? Pressure goes down, flow goes down. The ones that have the single core O-ring follow the green line. And the one that's got two cores in it at 1.2 gallons per minute, as shown here, follows the gold line. It gives you the same flow rate that you bought all the way down, almost all the way down to 15 psi at the faucet. That means you don't really care what the city pressure variances are. That problem goes away. It solves lots of things that go odd in plumbing while you build buildings. We really don't know exactly what the pressure is going to be at the other end until we actually get it built. Because we've measured the pressure loss for modern pipe and fittings, we can predict it better now, way better now, and I'm more concerned about the last mile, the last 20 or 30 feet, because everything's smaller diameter at that point. That's what I focused on. Okay? Yes, sir. So how would you look for pressure compensation when you're buying it? Well, first you open it up and you look inside, and if you see an O-ring that looks like this, you're in good shape. Okay? I know that sounds crazy, but that's the way to verify what you've got. You can go to your big box stores or your supply houses and say, I want one of these pressure compensating flow regulators. The company that makes them for almost everybody in the United States and for the European brands is called Neoperl, Neoperl. They sell through distribution or big box stores, retail only. I just learned last week that all retail sales will now have the dual core regulators for all flow rates. These insert into any faucet. You can take out the ones you've got for a couple bucks, put one of these in, and check it. What's even more interesting is that there are 3 stream patterns you can get for our standard faucets. When I say faucet aerator, do you hear champagne bubbles? It feels bubbly. Has anyone ever seen a faucet that comes out with a clear column of water, right? And has anyone seen the little shower heads? Okay, those are the 3 stream patterns. You get to pick at any flow rate. This technology is amazing. Okay? All right, we need to move. We're getting there. Heat pump water heaters. I promised to talk about it. Has anybody installed a air source heat pump water heater yet? That's great. Brand doesn't matter yet. We're going to talk about the technology behind it. What does a heat pump water heater do? It heats water, that's nice. How does it do that? It cools air, very good. It sucks air in one side and blows it out the other side cold. In the middle, it tries to make hot water. Okay, what temperature does the air going in need to be efficient? I hear 60. Anybody hear a higher number, please? It's closer to 70. They're rated at 67.5 degrees. The UEF you see is rated at 67.5 and 50% relative humidity. Anybody live where you get those 2 numbers together all the time? You're looking at me like, no, of course not. Doesn't happen very often. Here, it was this week. It was here. But, you know, that's nice. That was this week, not next week. It's going to be different. Where do you put water heaters? Inside the house or out? I hear basements. I saw a basement. That's what down means. How about garages? Anybody got water heaters in garages? Me too. Anybody in attics? That's Houston. For reasons that escape me, they like to put water heaters in attics there. I get it, but I think we should put them all over the master bed. Just 'cause. All right, what else do we have? Where else do water heaters go? Utility rooms, right? That's good. Where are the utility rooms? In basements or garages, but not on the first floor of a 2-story house with a conditioned basement. We put water heaters where water heaters go because they've been there forever, and we're mostly doing replacement. The cold air coming out of the heat pump is somewhere between what? If it goes in at 70, it comes out 60 down to 50. Maybe the room gets colder, it comes out at about 40. And when you get too cold, it starts to stop. If your incoming air gets too cold, it just doesn't make the heat pump work very well. So most of these are hybrid units, and they switched into electric resistance mode. But I'm an energy guy. I want to be efficient. I don't want a COP of 1. I want a COP of 3. I want to get the benefit of the heat pump. Well, I want to make sure we do that as we build these out. So we need a thermal source for the supply. You have to have the resource. How many hours a day do you want the heat pump to be able to run as heat pump? All day, 24 hours. So if you put it in a room that has no new energy resource coming in other than what's here, eventually you'll run out of heat. Because the cold air is going to get discharged into this room. It's just going to keep making the room colder. Okay, so you have to make sure you have a thermal resource for the supply, and you need a thermal sink for the discharge, and they have to be equal. Gazintas become gazoutas, and you have to manage them both. Fair enough? For air source heat pump water heaters, airflow is the key, not the volume of the room. It's the only thing that matters when you go back and look at the physics. If you give me an enclosed space of about, say, 700 cubic feet, which is in a bunch of the manufacturers, some have 450 cubic feet, it's telling me a couple of things. It says that's all the energy I get until the room warms back up again. If you cool down a room for an hour, it takes at least an hour to warm it back up again, doesn't it? Well, it's not so bad with a heat pump water heater in it because the standby heat losses of the tank help warm up the room. I'm sorry, that wasn't what I was aiming for. I was trying to figure out how to run the heat pump properly, okay? So I have this dilemma. If I cool down the room for an hour, I got to let it warm up back up for an hour. That means I only get 12 hours a day to operate in heat pump mode. You said 24 before, didn't you? So it won't run in heat pump mode for 24 hours if you limit its access to thermal resource. Right? You have to make sure we have enough thermal resource. Oh, here's a good idea. We can have any room size we want if we put an electric heater in the room equal to the heat rate of the heat pump and turn them on at the same time. But we have to remember, that sounds crazy, but these are designed for use with indoor air. We're already using conditioned air to do it. I'm just suggesting one obvious way to make sure it's okay. If you don't want to put a resistance element in it, you have to run a big duct or a radiator. You've got to provide the heat in the back. That's great. What about dispersing the cold air out of the room? But if the cold air is going out of the room, how's the new warm air getting into the room? It has to be ducted. It's the airflow that's the issue, not the size of the room. Okay? I want to install heat pump water heaters in a space that they need to be in so they're serviceable. Has anybody come up to a water heater they had to service and you can't get to all the parts? Come on, we don't need to do this. We need to do a better job. We have to make things easy to work on. So, does the furnace throw off enough heat to help augment this? The answer is yes. But where I live, my furnace and air conditioners in my attic and my water heaters in my garage are not related. They're sort of in different.
Next to my furnace helps.
It helps, but I actually wouldn't just worry about the heat coming off of it. I would want to use the return system to suck in the cold air so that I now disperse the cold air around the whole house and it doesn't make any one spot cold. Here's the problem. We have dew points. If you go below the dew point, you get condensation. That's what we teach in building science, right? If you have condensation long enough, you'll end up with water damage and mold. You pick. Neither one's good. Isn't that what we're trying to prevent? Most of the plumbing industry doesn't understand all of this building science. They just put in water heaters. How many plumbers are here? Great, 2, 3, I saw 3. That's like 5% of the crowd. We need more of us here because the science of building correctly applies to our work all the time. Occupant comfort matters. You don't want to blow cold air on people's feet. You also don't want to blow cold air on your thermostat. Right? You're blowing 40-degree air on your thermostat. It's going to say it's cold, but you don't need air conditioning or heating right now. It's going to turn on the heater. Oops, it's summer. Why would you do that? Right? We don't want to confuse the building systems. Let's move on. All right, now let's talk about right sizing. I think we're making good progress. The red line is the conversion between WSFUs, water supply fixture units, on the bottom, and gallons per minute on the y-axis. In the Uniform Plumbing Code, the International Plumbing Code is almost exactly the same line. Everybody all good? Notice the black dots. Those are 20 apartment buildings around the country, ranging in size from 8 to 384 units. Notice that the black dots aren't very close to the red line. That's the prediction and the plumbing code for the diameter of the pipe serving that building, for the gallons per minute the building needs, and ultimately it becomes diameter. They're way off. Let's zoom in on the left. You can see the water supply fixture units on the bottom. You can now read the letters in the round dots. And you can tell that even the lower left-hand corner of this graph, less than 300 fixture units, there's nothing close to the red line. The water supply fixture units in our codes and standards were published in 1940. It's called the Hunter's curve. Nothing flushes or flows at the rates it did in 1940. Why are we still designing pipe that way? Right? We have to design it for what it's going to be, what it's like. So let's look at this. There's a chapter in the Uniform Plumbing Code, Chapter 6, and then there's an appendix called Appendix M. This is part of the Uniform Plumbing Code. It's also separately published as a water demand calculator standard. It's accessible and usable in any jurisdiction in the United States. Okay? And it's designed to apply to residential new construction or major renovation from the meter all the way to the branch to the last fixture, right? Not the twigs, everything up to those. This is what it looks like. It's a downloadable calculator. There's one that goes on your phone as an app. There's another one that goes on your computer. Currently, I think it works for all types. And it allows you to put in on each number of fixtures you're interested in, flow rates up to the maximum shown, and then you press go. And it gives you an answer in gallons per minute, what the peak estimate would be based on modern flow rates and probabilities of use. This is what we're looking at the benefits are. The little black dots at the bottom are what you've seen before. There's now 22 buildings in this set. We have some new ones from Minnesota. The blue lollipops are the water demand calculator predictions, and the red lollipops are the plumbing code predictions. Here's an example. 35-unit apartment building. The plumbing code said it's going to expect 70 gallons a minute coming in a 3-inch main. 3-inch meter, 3-inch, everything in the mechanical room. Everybody good? That's pretty typical all over the country. The water demand calculator calculations came back at 15 gallons a minute. Instead of a 3-inch pipe, they needed a 1 1/4-inch pipe. What do you think? Does that cost more or less to build? It costs a lot less to build. And it tracks all the way from the meter charges all the way through to the last fitting you have to put in. 3-inch fittings cost a lot more than 1 1/4-inch fittings do, let alone the length of pipe and the ease of installation. It's a huge win in first costs. There's a report on it. That QR code should work. I checked. But don't worry, the other you should be able to get it. We use this report to make a proposal to the state of California to adopt the water demand calculator appendix into its plumbing code. It took effect July this year. We're working in the state of Minnesota to help them adopt the same provision. They have the same code. So we're helping them figure out if it makes sense to them to do it. Questions? It's your turn now. Someone has a mic. If you have a question, let her come down the hall. Anybody have a question? No questions. In the back, you get him and then come over here. We'll get you. Go ahead.
So so the flow rate would depend on your supply main.
Okay.
Does that calculate? So if you're calculating your system 1.5 for toilets and all that stuff,
Yeah.
and your lavs and your showers, you split them because you have hot and cold.
Right.
Your water heater's in the basement and you go to the second floor. But if your supply main's 3/4 and you do your calculations by the pressure that's coming in the building versus your loss going up, then your supply main would have to be bigger.
It depends on your starting pressure.
So
Okay, if your starting pressure is low, you have to make the pipe big enough to make sure you have enough at the last fixture.
Volume,
Pressure,
pressure.
okay?
So volume has nothing to do with,
Virtually nothing.
okay.
We oversize because we don't know, and we oversize again because we're afraid, and we're using numbers from the 40s. We can stop some of that. What I recommend we do, you're a plumber, right? I can show you how to build a mock-up at your shop. And you can literally put things together and predict the pressure loss of the situation you're describing, except for elevation. Add the elevation loss, as long as you have enough, you're good. You can build it and test it.
Does elevation change by your actual elevation of your city?
No, not so
You
much.
know what I mean? In Florida, Wyoming.
No,
where-
what matters is what's the starting pressure at the service entrance,
Okay.
okay?
I'll get with you after this.
Thank you. Get with me after. I saw a question in the back over here. His hand was up next, and then yours.
I was just looking for a best fit resource for finding all this stuff and making sure we can design accordingly.
You're looking for a best fit resource so you can design accordingly. I wish I had a book, because that's what we're going to have to go to. In the meantime, there's a bunch of videos. Go to my corporate website. You can watch me being recorded doing a 2-hour version of this class. You can watch it as often as you want to. You can repeat this class, but there's a lot more in the bigger version. Passive House Accelerator recorded me a few years ago doing 2 things, the right sizing piece we just discussed, and architectural compactness. I think we're going to want to do another video soon on what we call, why your shower feels wimpy and what you can do about it. Those would be the best resources at the moment. You are welcome to reach out to me. I'm a design engineer. I help people work through this stuff. Yeah, I got to get paid for it all. That's fair. But that's the way we work to help everybody at this point. We don't have all the resources in one spot, the way you're looking.
Thank you.
Over here, a question over there.
Yeah, so I just wanted to clarify. So, you remodel a shower, and they want 2 shower heads now, a rain head, 4 body sprays. You know, the challenge is you can't run, and they want to run all of them at once. They want a car wash. Challenge is can't do that, all the flow rates. You're saying, and the solution with our plumbers has always been, we got to run bigger pipe. You're saying that's not
No,
necessarily the solution.
if you do that, you have to run the pipe to match.
Yeah.
So yes, you have to run the right pipe to match the flow that's desired. I'm not going to put a value judgment on the rain wash, the car wash shower system, right? But if that's what the customer wants, you have to design accordingly. By the way, the water heater that's in their house now isn't big enough. You need more than that. So the math is very simple. A gallon a minute takes a gallon a minute out of the water heater. 10 gallons a minute takes 10 gallons a minute out of the water heater. Okay? If your water heater is storage, you only get 70% of the volume in the tank to begin with. So a 50-gallon water heater gives you, at 10 gallons a minute, a 37-minute shower. Sorry, it's not long. Huh? 3.5 minutes. It doesn't get that. That's not what they wanted. They wanted to be there for 30 minutes. So they actually need a much bigger burner and a much bigger storage system. Yeah, right, and on demand you want to go 3 times bigger than you think because you want to be in the sweet spot, because otherwise you have too much pressure loss. In the back, and then I'll come over here.
Can you talk about distribution models? So traditionally we do trunk and branch. There's options to do home run.
Right.
And then you've got like the multi-port T type of system that Upador talks about. How do we size or consider the distribution model given the lower volume piping that you're talking about?
I work backwards. Tell me how long you want to wait. Work from that. If you want to get, I use 10 seconds as a good walking around number, okay? We've talked about how hard it is to do better than that, and we know how we can, but let's just use it. It means you can have about 10 ounces from the source to the use. In half-inch pipe, that's about, in PEX, it's about 8 feet. Copper, it's about 6. All right, it's a bit more than 1 cup, right? So home run is going to be tough in half-inch, but if you can use 3/8, you get double the length. Does that make sense? And so we've got it goes back and forth for the distance. You've got to decide on distance. time. So now you're given the building. After you haven't designed it, you're giving something to make work. How do we make it work? In general, there are 5 ways of distribution. You can have a circulation loop. You can have a water heater for every bathroom group. Cool, I didn't want to buy one, I got to buy 2. I got 3 bathroom groups and a kitchen and laundry. I have 5 water heaters in the house. That's great for some folks, but now we've got maintenance and space problems, right? You can do all those things. You can put a recirc loop in and keep the branches short, twigs short, right? You could put heat trace on the pipe. There's lots of ways to get there. So home run manifolds, you're putting everything at the beginning and going outwards. A mini manifold, you put in line near the fixtures in question. Anybody ever seen a bathroom with side-by-side sinks? You know who's going to get the sink with the shortest time to tap? It's not you. Make them the same. Sorry, go ahead.
Yeah, I want to get clarification on pressure drop with PEX and the fittings versus copper. One, let me understand why, and then 2, why is PEX like so popular? Why is everyone running? I mean, I know there's reasons it's easy to install and stuff, but if it's worse for that, getting hot water to your devices, why are we doing it?
Which one costs more per foot? That's 90% of the reason.
An issue, and they're still using PEX.
Right, so they're still using PEX even though price might not be an issue for some folks. It's really easy to install. So labor goes down, but I can show you how to install copper just as fast as PEX. It's lack of understanding about the choice.
It's prioritizing convenience over performance.
Yes. There's a certain amount of priorities in them, not necessarily the right place. Okay, so.
Reason to use PEX for a performance reason is what it sounds like.
Which one loses heat more quickly? Uninsulated copper or uninsulated PEX?
Copper, I'd imagine.
You'd imagine copper. Nah.
Really?
Really. Think about it. How do we build a building? This is a fun one. Could you hold this, please? Thank you. How do we build a building? Foundation come up. The pipes are rarely strapped tight to the building. Is that correct? If we strap pipes really tight to the building, it's called warm floors. We're trying to make radiant heating of some form, right? We're not trying to do that with our plumbing. It typically goes across a rectangular piece or through a rectangular piece, a couple inches long, and it barely touches very much, right? So it's a thin line of pipe touching a flat surface that's not particularly conductive. We all good? I agree that copper is a much better conductor than plastic. The temperature of the water in the pipe gets from the inside of the pipe to the outside of the pipe like this. We'll call that a millisecond. Very, very fast. Plastics are 100 to 1,000 times more resistant, so it takes up to a second for the heat to get to the outside of the pipe. But after 1 second, they're the same. So what are the mechanisms of heat transfer? There's 3 of them. What are they? Conduction, convection, and radiation. These are the same outside diameter, is that right? They're going to have essentially the same convective term. Not identical, I'm not saying that, but they're awful darn close. Conduction to the building is almost exactly the same. There's very little of it, right? And they're not conducting through the material. They're taking the temperature of the outside surface going into the next surface. There won't be much, and it's similar. What's the third term? Radiation. What's the emissivity of copper pipe or plastic pipe? Well, I'll have to go look it up, right? Most of our world has emissivity of about 0.9. Some special materials, you know them as low-E glazing materials, have low emissivity. What do they use as the materials for low-E? Metals. Which metals? Silver, aluminum, copper, and gold. We use gold in the space program. That's where we started using it. Okay, we don't put that on pipes much, but we, gold, it's good. Copper's emissivity is about 0.1. So the third term is very, very different. This is 0.9-ish, this is 0.1-ish. This cools down more slowly when it's uninsulated. Who knew? Insert fittings. So if you stick something in the middle of the waterway and make the hole in the middle smaller, you're going to restrict the flow. Restriction to flow matters a lot more when the pipe is smaller. That's one of the reasons I started my research at the small diameters. I've measured pressure loss down to 1/8-inch tubing. You want to slow something down, just put a curlicue of 1/8-inch tubing away. It'll slow everything down. I'm not proposing that, but you can fix whatever you want, right?
Realize time here, but
So the flip side is that if you design it correctly, PEX uses far fewer fittings. That's correct, but the pressure loss per copper fitting in half-inch pipe is about 0.05 psi for the same flow rates, where in PEX it would be 2 psi per fitting, up to 2. Home running. Right, so you can eliminate fittings because you can curve PEX pipe. I agree. I agree, absolutely agree. My rule is there shall be no fittings other than the beginning of the pipe and the end of the pipe. No 90-degree elbows. Ideally, none. In copper, the best 90-degree elbows I have for you are these. Long radius sweep you can buy at the store, or you can bend your own. We call these swoops. I trademarked the name. It's a swoop. You can use it. You just got to give credit for using it. Okay? And it's a long radius sweep. By the way, it's closer to the hypotenuse of the triangle. Closer to the hypotenuse, the shorter the distance. Short distance, remember, distance and diameter all matter. This shape, this long radius bend or the bend supports you get for PEX, has no extra pressure loss other than the length in itself. It's as though it were straight pipe. That's pretty darn good. It's hard to do much better than that. All right, a couple more things to share. I want to talk about drain water heat recovery. It comes up a lot in conversations. It's a great idea to capture waste heat before it runs down the drain. We do the same kind of thing with air-to-air heat exchangers, where we capture the energy in the air before we let it out again. We spend money conditioning it. All right? You have to decide where you're going to put it. Anybody house with basements? Raise your hands again. Water heaters in the basement, so does the drain comes to the basement, right? Are all the showers sharing the same drain by the time they get to the basement? Maybe. If they are, that's the best place to put this, because you're going to capture all of the waste heat that comes down the drain. They're the most effective when it's a shower. It's a continuous use that's going on, so you need simultaneous heating, and it's simultaneity that matters here. Water running down the drain and new water coming in. That's called showering. Okay? The best case is to connect the output of this, the warm water, to both the water heater and to the shower system. Not to your sinks, to the shower. That's the best case. You don't always get the best case because things are far apart. Okay, but that's the best way to do it. On a good day, if you've designed it right, these will pick up half the temperature difference between the temperature coming in the drain and the cold water coming into the house. So if it's going down at 100 and coming in at 60, you divide, that's 40, divide by 2, you'll get about 80 degrees coming out. That's called Phoenix. Yes? Even though the water in the
drain pipe's not going to be filling the drain pipe?
So it doesn't have to fill it. It sticks to the side.
Okay.
Water is very clever. It's sticky and slippery. It's very confusing.
Say someone is just washing their hands, or it's, you've got 54-degree water coming in from the ground, from your supply. It still adds a little bit to
it does,
water.
but
it's not a shower, or
it's almost useless for sinks. It's such a short event. It's hard to justify. You won't feel it. Okay? So could you do it? Yes. My recommendation is not worry about it. Okay? We talked about circulation loops for a little bit earlier today. Look, if your water heater's over here and your furthest fixture's over there, it's really hard to do anything other than figure out how to heat the pipe with electric heat trace. You can do that. Strap the heat trace to the bottom of the pipe, insulate around it all, you can make it work. Okay, it's doable. Plumbers and electricity don't like to go weather often, so it's an interesting challenge. Can be done, it should be done. It's a good choice. Mostly we put in circulation loops, right? So here's the question. What's the most efficient way to keep the loop full of hot water shortly before a use? Yeah, so we've defaulted to 24/7 because we don't know when you're going to use hot water. Okay, that's the most energy expensive way to do it. But that's what we do because we don't know when you want your hot water. I don't either. But I know how you know it's time to take your next shower. Right. Does anybody have a routine they do while they wait for hot water to arrive? What do? You turn on the tap. What do?
Put my phone away and brush my teeth.
Right. You turn on the tap, check your messages, put the phone away. What does it say to do?
Sometimes I'll brush my teeth.
Brush your teeth. So it takes about 1.5 minutes to get hot water. Is that about right? We've never met, have we?
Yep.
Pretty good. What about you? Someone over here. You? Upstairs shower in his townhouse feels like a couple of minutes. It's all predictable. I've shown you the math this morning. You tell me how long it takes, and I'll tell you how your house is built. It's a math problem. You tell me how the house is built, we'll tell you how long it takes. It doesn't matter. They're interchangeable numbers. Here's the thing. I do not know when I plan to take my next shower exactly, but I know it's probably tomorrow morning after the alarm goes off. What if I had a button next to my alarm clock? What if I had a button on my phone, because my phone's my alarm clock, that told the pump to turn on when I got out of bed? By the time I brushed my teeth or went to the bathroom, hot water would be in my shower. I didn't run any water down the drain. Sounds pretty clever. You want to hit the button 20 times today? Be my guest. Go on vacation? Be my guest. Doesn't matter. It adjusts to your schedule. But you have to put the mechanism in anticipation of the use. If I put it at the sink right next to the shower and I push the button and get into the shower, it won't be hot yet. I had to bring it from the water heater 8 miles away. It takes time. This is the best we've seen for control strategies. They're the guys who got me into hot water 30 years ago. I'll end with this. I received a phone call when I worked for the state of California from this guy says, how long does it take to get hot water, the furthest fixture in your house? And I said, I'm not interested. I was working on space conditioning. All the stuff we teach in building science, I was doing back in 1992, 1990 as well. Okay? He calls me back every month for a year. Finally, to make him go away, I got up one Saturday morning with a bucket and a stopwatch, and I measured how long it took to get hot water at my shower. It took 4 gallons in 4 minutes. I had a 1 gallon per minute shower head. 1 gallon per minute, 4 minutes equals 4 gallons. That math is good. What's the problem? I could see my 3/4 inch copper pipe sitting right above the insulation in my house, because that's how they built it that year. I'm pretty good with math. There was less than 2 gallons of cold water sitting in that pipe before I turned on the tap. Why did it take 4 gallons till hot water got there? That's what I couldn't figure out. Look, there have to be losses. Double just sounded wrong. That's what put me on this journey and why I'm standing here today. I've been trying to solve that problem for us for 30 years. You've been a great crowd. Thank you for your time.
It's been a great week here at Build Show Live in Austin 2024. I want to thank one of our project underwriters, Polygaurd, who is providing this content from our classes, which were amazing in client management, building durability, and building science, where Polygaurd has been a leader in air and water management for a long time. We've used a lot of their below-grade water management solutions, but they brought out some great new stuff from their termite prevention to their air control products. Polygaurd's been solving things for builders for a really long time, and we're grateful that they're still working to make our lives easier every day. Thank you to Polygaurd, and thank you for your continued support of our educational content.